All right, so we're talking about application performance today. I'd like to start off with everybody think for a second on a application that you used where you clicked on something and nothing happened for 5 or 10 seconds. All right, does everyone have the app that they have used in the past that has that experience? And raise a hand, how many people currently work on that app? Yeah, okay, that's awful, right? It's especially like, and also, how many of you guys actually feel bad about it? You know, yeah, well, you all should feel bad about it. It's partially your fault, but hopefully after today you'll have some tips and strategies for things you can do in order to make your application a little bit snappier. Because at the end of yeah, nothing kills the user experience than just a sluggish, non-responsive app. So a little bit about myself. Software engineer. I've been working in the field since 2009. I've been at Dougherty Business Solutions since 2015. I've primarily been .NET, but I've kind of moved over to Node and AWS about 4 or 5 years ago, and it's a lot of fun. But where can I get some answers from the room? How would you guys define application performance? Not everybody at once. Speed. Okay, to who? To the user. Thank you. Does it matter if the code itself is fast? Maybe. Maybe. Depends on the use case, right? So how would you say, how would you differentiate between like application performance as perceived by the end user versus code optimizations where you're trying to make the code run fast? What's that? They go hand in hand, sure. But do you have to necessarily optimize all the code in order to get fast application performance? Yes, yes, we'll get to that. Yeah, like it's definitely something you want to do, and so it's definitely a goal, but you'd have to, obviously we're all busy, we got a million features to deliver, we don't have time to be optimizing every line of code. But if we'll get to that later in the slide as far as how you can prioritize the things you look into. So high level, what we're going to be talking about is just performance, like what does it mean, how do we get it on a high level. Then the different types of optimizations we can do. They fall into 2 main categories, I/O and CPU styles of optimizations. And then we're going to cover database queries because of those sluggish applications, how many of those were caused by some database queries just taking forever to run? Probably, yeah, like half probably, right? Or 90% actually is more likely. How many people have seen this before? 1, 2? Well, now you've all seen it. And so you should be able to, well, not necessarily memorize this, but kind of have the basic idea that not all code is equal. Some code, especially from a performance perspective, some code is so fast that you really kind of don't care how many times you're running it. Like L1 cache miss hits, and let's see what else. Mutex lock, unlock, like these are nanosecond operations, right? Unless you're working on a graphics or a driver or something really low level, you probably don't need to work on optimizing these kinds of operations. But within computer science, one line of code depending on how it's used, how much abstraction is behind that one line of code, could be orders of magnitude difference. And so what's being demonstrated here is that there are for these different classes of time it takes for the computer to do a task, it takes exponentially more time. So in this case, for one blue is equal to 100 greens, and 100 greens is equal to one red. And so if you're looking at 10 reds, so it's very important that whenever you go through this exercise of, oh, my application's slow, what am I going to do about it? Find the reds. Those I/O calls and those database calls and those reads from the file system are definitely going to get you the biggest bang for your buck as far as optimization time or actual benefit. And before we even talk about application optimizations, we really should address the elephant in the room that if you're trying to accomplish a task that's very inappropriate, and you're going to have a bad time. So for instance, if because of the design of your system, you have 1,000 microservices, and in order to show the screen, you have to call out to 200 different services in sequence, you're not going to be able to do that. You're not going to have a good time. It's like trying to cut down a forest with a hand axe, right? So don't put yourself, ideally you shouldn't put yourself in those situations where you have to optimize some horrible architecture that just is not well thought out. And but I would recommend that when you are developing your application, if you have reasonable layers for it, like you have a database tier, a business tier, a UI tier, that will help you isolate what particular parts of the application are misbehaving and taking forever. So that's definitely good advice, and not only will that help you organize your code, understand it, but it also helps just figuring out why is it so slow. So it's good practice generally. But yeah, so then when you're designing your application, these are the things you should be thinking about. Like, I mean, everybody loves microservices, but every API call involves the network traffic, and that's just going to be inherently slower than doing something inside the process. There's just no getting around that. So those trade-offs should be taken into consideration. So for a specific use case, you should, if it's for a screen that's going to be shown to the end user, it shouldn't require chaining 2 or 3 or 4 web service calls. That's just bad design. And so also you'd be considering which use cases are most frequently occurring within your particular application and the thing. And because if different scales require different infrastructure, right? Like a database might be just fine as a queue if you have thousands of rows or tens of thousands of rows an hour. But if you're processing millions or tens of millions of whatevers, orders usually is the the stereotypical example. But if you're processing millions of orders every minute, you probably should be using a queuing solution like Kafka or something, right? You really shouldn't be doing that in the database. Databases are not message queues. And on that note, is it possible you can this is something you want to work with your users for, or your product owners for? Like, does this use case require that a user be sitting and waiting for the thing to finish? If it can be done in the background and just they receive an email saying, hey, the expensive task 1, 2, 3, 4, 5 completed on such and such date, if that's acceptable, that might be a way to sidestep a need to go and through a risky and problematic optimization. So if you can, I love doing like avoiding performance problems rather than dealing with them directly. Because theoretically, all the user stories are negotiable, right? You guys have never gotten mandates that such and such must be done in such and such way, right? Never? Never, yeah. And so, like that brilliant lady over there explained, that the primary way that the perceived performance of the application is measured is how snappy is the UI, right? Like, I know there's a lot of back-end devs that are like, oh, well, who cares about the UI? But honestly, that's the only thing that people actually interact with, and that's the primary way that they'll say that, okay, this thing's junk. Look at it, it can't even load the screen without collapsing on itself. And so, but for the use cases on the UI, these are good general recommendations for you. So anything less than 0.1 second, don't even bother optimizing it. That's so low, they can't even notice any improvements past that point. And if there is a delay without a spinner or a loading icon, it's got to be less than 1 second. If they click on a button or interact with the app in some way, and it doesn't respond within 1 second, you'll actually break their concentration and cause them to feel frustration, and which will be directed at you in the user acceptance testing meet. And so, and so if you have an operation that you know is going to take a while and you know it's probably not going to get done in a second, put up a spinner, right? It's not that hard. Just conditionally render out a spinner after you do that web service call. It's not going to kill you. And but a spinner that goes for more than 10 seconds is just asking for trouble. That's maybe even worse than not doing anything. They'd probably prefer it crash than like just spin forever. So keep that in mind. And so if you know that, hey, it's going to take more than 10 seconds, either do it asynchronously, hey, we'll send you an email when the task is done, or have some kind of loading indicator to let them know, yes, we are working on this task, and it's going to be done sometime. Well, we promise. And even if the loading indicator is fake, right? I'm not sure if you guys have heard the story of like Airbnb where they just show a lot of random tasks that are being done, but it's not actually doing those tasks. It's just appearing busy. But yeah, totally do that. That's fine, right? They won't know the difference. All right, so I have some. Caching is a really good strategy. It's something you definitely should consider. It should be a little bit measured, or not. Just cache all the things. It's fine. But no, seriously. Caching is a great strategy, but it's one of those, it's the only thing harder than that is naming things. So, because you got to do, like, the cache shouldn't be there indefinitely. It's got to be invalidated at some time. So you got to have some kind of strategy for automatically invalidating the cache because that's the source of bugs, right? It's like you're showing data to the end user that's incorrect. And that actually it's a potential source of bugs. And so based off the particular thing that you're caching, you'll have to decide as far as what's an acceptable amount of latency should be for that data item. Okay, and so, so that's advice for setting up your application so that you don't have to do optimization. So my general advice is to, try to avoid it as much as you can because it's pretty scary. All right, so but the definition we're going to work with today as far as what optimization is that you're taking code. That's correct. It passes its unit tests. It's readable. You understand what it does well. You understand what it does well enough that you're willing to rewrite it to make it run faster, even if that would potentially hurt readability of that code. And the first step for any optimization process is to don't do it. Put it off. Maybe is it really that important? Is this like it's 2 seconds to load this screen. It's not that bad. Oh, okay. Yeah, I know it's 2 seconds. All right, but it's 1.5 now. Is that okay? No? Okay. All right, well, now I'm going to have to actually get in there and dig in and try to make it work. But before you just go in and start ripping out code, try to have some kind of objective measure that you're trying to meet. And keep in mind that it will always be, the context of the application itself is always hugely important because every application uses data in a slightly different way, and it's not always obvious that regarding what exactly the problem is. So definitely have some kind of goal and get a tool to measure against that goal. Every platform has a profiling tool of some sort, so yeah, take your pick as far as which one works best for you. But pick a tool, please. Don't just go randomly changing the code. You could well be making it worse, right? It's like there's no way to know. No way to know. Okay, so I would definitely recommend you first take a look at within the code, this chunk of code that's not performing well. Where are my web service calls? Where are my disk reads? Where are my database calls? Because those are like the most expensive operations that can be done. And if you're doing way more of those than you're expecting, then that's an obvious and easy fix you can do. Okay, how do I batch up these calls to not do so many of them? Or how do I do them in parallel? Well, yeah, I'm getting next slide. All right, so one thing you can consider for IO-bound operations is multi-threading. All right, so roughly, do I have any guesses here as far as which one of these two, which one of these two ways is faster? The top one. Well, yeah, so there's one that does the work in serial and another one that does it in parallel. So it's got 10,000 items, and for each item it waits 100 milliseconds. So roughly, like just shout out from somebody, roughly how long should the serial case take? Yeah, just 100 milliseconds times 10,000. I did the math here, so I already know it, but it's 16 minutes roughly. And depending on how many threads can be spun up, what you would expect, the second set of code, you'd expect that to be 4 to 6 times faster, because this is trivially parallelizable, right? This code literally doesn't do anything. So it's definitely not bound by the amount of processing power available on the CPU. And so that's an easy trick. Okay, so for this example, can I have any guesses as far as what the difference between these two, these two are, and which one might or might not be faster, and why? Hash set, thank you. Why is the hash set faster? Come on, I know you guys, how many people took basic data structures in computer science? Constant time access, thank you. So in this particular case, on line 3, what's the order of magnitude of that contains call? Is it constant? No, it's not constant. It's n. So that means for this chunk of code, you can take this chunk of code and run it in C#, and it'll be noticeably slow. So for the first chunk, it takes 100,000 records, and for each one of those records, does a search against the second list of 50,000 records. So that's 100,000 times 50,000. That's n squared, basically. So it's just a slow chunk of code. Well, the second example uses n operations in order to build up the hash set, and then n operations to perform the where clause against it. And then for each item in the where clause, it does a constant access to check whether that item is in the other hash set. And then that all evens out to n. So in this particular case, that's the difference between 100,000 operations versus 100,000 times 100,000 operations, which starts to add up when the numbers get bigger. And so these are common data structures. Most of them are kind of not that useful most of the time. Just throw a hash set at it. It'll be fine. Just use hash sets. It's the answer to leak code interview questions because it's true. Right? We don't need anything else. Just hash sets. It's fine. OK. I guess, are there any questions about those IO-bound or CPU-bound optimizations? Are there other ideas that I missed? Anything? No? Cool. All right, so how many of you guys use a relational database? Really? Huh. I guess they're not that cool anymore, huh? Everybody's just on, I personally am using Mongo at my job right now, but I've used, I was expecting at least half. That was only a quarter. Or are you guys just bored? Yeah, that's fine. But, OK, for those of you that don't have to use relational databases, that's, I guess you can leave now, because that's the rest of the talk. But for those of you that are interested, the rest of the talk is going to be about query optimizations, because while those other things happen every so often, where it's the actual code that's slow, by far the most common problem with application developments is there's just some query that just takes forever to run. So, and SQL is a great language, or I still think it's a great language. Like some ideas are so good that once they get invented, they just can't get improved anymore. And SQL is one of those ideas. It's been around since the 70s because it's got good fundamentals in set theory. And even though it's not cool, but I still think it's a great trade-off between flexibility and correctness. So overall, I think it's a pretty good tool. But unfortunately, in order that abstraction that's provided to you by the SQL querying language is great when you don't really care about the internals of it, right? Just, hey, database engine, go get me this data, do these operations and get me the data and format it in this way and order it by this and give me the data, right? And then the SQL engine does its magic and gives you the data. But actually, but if you start running into performance problems, that's kind of not be good enough. You're going to need to know a little bit about what's going underneath the hood in order to be able to identify and fix these slow-running queries. But I'm here to help, so you guys should be all set. But my primary piece of advice for working with query or for making queries run fast is to make sure that the query that you're writing has indexes to support it and are being used. So that sounds easy, but it can be, depending upon the code that you inherit, that may not be obvious to suss out exactly what is going on. And so the first thing that you'd want to do is, okay, I have this query that I want to make run faster, which is not a which for a lot of applications, just figuring out what the misbehaving query is can be quite painful. So keep that in mind when you're using an ORM. Is sometimes if you're doing, they can generate just crazy SQL. So if you're using an ORM, make sure you have a way of inspecting the SQL that gets generated so that you can at least take a look at it, right? Even if you don't have to physically write it yourself. At the very least, I want to be able to look at it to see if it's crazy. And also, like, obviously, prioritize, right? If it's a table that's got 1,000 rows in it, it's really not worth putting an index on and spending any of your time trying to figure out how to decrease the query time for this particular table from, 80 milliseconds to 70 milliseconds. It's not a good use of your time. I also strongly encourage having a dedicated data layer within your application. It'll make it easier to pinpoint which chunk of code is responsible for making these queries and make it a little bit easier to isolate it down to specific functions or queries within your application code. And if you're not exactly sure what query you should be optimizing, a last-ditch effort you can do is to just spin up the database profiler for your database tool of choice to see what's coming through the wire. Like set up a specific, you filter down to that specific user for your application and just see what's coming through the pipeline. But that's less than ideal. Okay, so how many people here have heard about database indexes? Hopefully everybody? Yeah, okay, cool. Does everyone know? Yeah, but on a high level, they're like a phone book. What's important about them is that they're in order. That's the magic. And because they're in order, they're represented within they're physically stored as a binary tree, and then you can use a binary search in order to find items out of that database, out of the index. And which has a computational runtime of not n, but log of n. And log of n is huge. It's just really efficient. So like I said, there's a lot of magic that goes on underneath the hood when you submit a query to a database. What it'll do is it'll take that query, and then it will parse the query and then generate what's called an estimated execution plan. All the execution plan is just the detailed step-by-step operations that the database engine has to do in order to find the data where it's physically stored and get it out of the database. And then after the relational engine has generated the plan, it'll be passed to the storage engine in order to actually go and get it. And then once the storage engine actually goes and gets it, it'll pass it back to the relational engine, and then that key will, and then the hash of that query will be used as a key to cache the actual execution plan from here on out, and we'll get into why that's important later. So when you're trying to evaluate whether a slow query is running, or why a query is running slow, definitely one of the first things you want to do is just pull up the query plan. Like every database engine will have an option to be able to say, okay, take this query and show me what the execution plan is. I'll demo that at the end of this talk. But when you, all right, but then, all right, I'm not sure. How many people have looked at a query plan before? Right, and how many of you have known all the stuff that they show you on those query plans? Not very many, yeah. So, it's kind of a lot of stuff, and you kind of get used to reading them. And the main thing that you want to look for is, obviously, if you pull up, the query plan for a particular query, and the database engine has big red flags, and it's saying, "Oh my God, I can't believe you tried to make me execute this code. It's so bad." That might be something you want to look into, maybe. And you also, but within the query plan, they'll generally have how many rows were processed by each operator. And so obviously, you'll want to focus on the highest cost operations first, because that's where you'll get the biggest bang for your buck. And if your query profiler supports a visual representation of the query plan, if you ever see really changes and transitions, that might be a good place to look into to see why is there so much, or why a row is getting filtered out, or why is there so much data being pulled in. And also, if you pull up the query plan and you can't even see it, there's so many operators that you zoomed out from 10,000 feet and you can't even make out the lines anymore, that might be a problem too. So if an ORM might generate crazy SQL every so often, and so you definitely want to keep an eye on that. And then, obviously, the next biggest problem are if you're doing table scans against large tables. Obviously, a table with 50 million records is going to take you a lot more time to search through every entry in that table than one with 10,000 records or 1,000 records. And so when you take a look at your query plan, try to find the ones that are, the most expensive, the biggest tables, because that's where you'll get the biggest bang for your buck. Okay, so how many people think dynamic SQL is slow? Slightly yeah, I should have done that before I switched to the next slide, but that's fine. I don't think it's slow. I think it's great. And in fact, I've worked at some companies where they insist that all queries against the database have to be encapsulated in stored procedures. And I would kind of semi-disagree with that convention, just because while the creation of the execution plan is not necessarily insignificant, it's also not really that significant either. By far the biggest problems with most queries is just that they're trying to pull in too much data, and there's not an index to support that particular query. If you have an index, most queries will be fine. And you definitely wouldn't want to write a query like this example here, because since there are null checks for all of the columns in the query, the optimizer will not actually use an index for these columns, even if an index exists, because the optimizer has to optimize for the worst possible case where all three of those are null. And so it'll do a full table scan, even if it could have used an index, even if there is an index to support that table. So this right here, I would argue, is an anti-pattern. You need to be better off using dynamic SQL. Yeah, and how many people write code that can be exploited by SQL injection attacks? Anyone willing to admit that? No? Okay, only me? Okay. Only once, and plus, it's a line of business app. No, we don't have hackers. It's fine. But yeah, generally though, you shouldn't be using you should be using bind variables within your SQL statements for the simple reason that not only does that help, not only is it not sloppy and not protects you from SQL injection attacks, but it also makes it so that the actual execution plan can be gotten from the cache. Because if you put the actual data into the query, it'll mean that it won't be able to reuse that execution plan, which again isn't necessarily huge, but we're talking 50 to 80 milliseconds, I think, if I had to put a rough order estimate as far as how long that takes. But please don't challenge me on that. I totally hallucinated that. So another gotcha that you can run into with your queries is that if you apply a function to a column, the optimizer will not be able to use the index for that column, even if there's an index that exists, for the simple reason that the result of executing that function on that column might not necessarily be the same as the order of the data in the index. And so if you're applying a function to a column, it's going to do a full table scan. It's not going to use an index. So if that's important to you, if you want to use an index, don't do that. And you can filter on using the like clause. But what's important is just where that wildcard is used, because the first time that the wildcard is used determines how much data gets filtered out. So in this particular example, when you use the wildcard for after WI, it was only able to filter down to all of the records that use WI. But if you use WINA, then that filtered it down to one specific record. And again, that's log difference in performance. Yeah, and obviously, so you do want indexes, and you want your indexes to support your most heavily used queries. But as on all things in life, a little bit is good, but too much, you can always have too much of a bad thing. And so in general, it's a good practice to index the data that's actually in the database, right? Like if you need to use computed columns, that's fine, but generally the original data is the best thing to index. Then you'll want to order the order of the columns used in the index actually is important, because and you'll want to do it by equality then by ranges. And so by equality I mean like IDs or names or specific things that when you use them in your query, you say, get me all the rows where the name is equal to Bob. And the reason for that is because those are more selective than the other kinds of other kinds of columns like dates or amounts or numbers, where you say, give me all of the employees that were hired between last month and this month, right? That's less specific than the equality matches. So when you when you create your indexes, it's a good general practice to filter out as much stuff as you can as early as you can in the index. And another neat little trick is that if you put all of the data you need for your query inside the index itself, you can save a lot of time because the database engine won't have to go out to the heap in order to get the actual data from for the actual row. It'll be able to use just the data that's contained in that index, and depending on the number of rows, that actually might be quite significant. So that's a good trick to get more make it even faster. But you know, obviously, as in all good things in life, you can't have it all. So you still have to be somewhat select. You still should be somewhat selective in the indexes you create, because for the simple reason that every index that you add makes reads that use those index faster, but they also make updates, inserts, and deletes slower. So depending on your use case, that might not be acceptable. It just depends. Okay. Any questions about SQL? Anyone want to argue with me about something? Okay. Okay. So here's the query that I'm going to optimize for you guys real quick, right on the spot. I've done it before, so you don't have to worry about me screwing it up. Let's see. But yeah, so it's a relatively simple data model, but it's got a fair number of rows in the database. Let's see, are you guys, okay. So the tool that I'm going to be using is pgadmin. And so this right here is the original query. So what we're going to do, okay, so I just ran it, and so this right here is actually the estimated execution plan. You notice how that was pretty much instantaneous. But then when I click here, it's going to actually run the query, generate the actual execution plan, and then show me the results here. Okay, what am I looking at here? And so if we take a look at this query, what we're doing is we've got employees, salaries, department employees. We're filtering by where the department name is equal to sales, and I know that what this means is that they're current employees, where they don't have the to date is like set to 119999 to represent current employees. And then we're grouping by their ID, birth name, first name, last name, department, and we're getting the top 50 we're getting the top 50 salaries. So what we're doing is we're trying to find, okay, for this fictional company, who are the top 50 paid people in sales? And so, okay, so the first obvious question is, okay, how big are these tables? So we got employees, salaries, department employees, okay? Let's take a, so I just throw a simple query to just do a count on those tables. Yeah, and that took eight and a half seconds. So that barely qualifies under my user interface guidelines. So these guys should have had a loading indicator. Yeah. I'll put in a pull request for them, or no, not a pull request. Obviously, I'm not going to do the work. I just want I want somebody else to do it. So, yeah. So in this case, okay. All right. So this employee table's got 3.3 million rows. This department employee table's got 3.6 million rows, and this salary table's got 3.1 million rows. Okay. So they're pretty hefty. Not too bad. And so, yeah, and so looking at this query, are there any thoughts as far as initial things that we might be able to do? Any red flags? Okay, no worries. Yeah, so, but okay, so what are we looking for when we're looking, all right, so here's the action. Here was the actual plan that was generated for this query. And what are we actually looking for? Well, the main thing that we're looking for is which tables are we doing, and are we using an index for those tables? And how do we know that? Well, within Postgres, it'll tell you the type of operation that was used in order to get the data out of the database. And so in this case, it's saying that they did a sequential scan on the department employee table, which is not good. That's one of those big tables. It had like 3.5 million rows. So that would be our first guess. Okay, let's try to find a way to add an index. And what do you know? I got one right here. I'm going to create an index. Okay, let's try running it again. You guys think that'll help? Maybe? I think it was, what, 9 seconds last time? 7. Okay. All right, so still doing a sequential scan. Sequential scan on department employee. Oh, but it's doing an index scan on salary, but it's based off the current to date. Okay, let's go ahead and create another index. All right, so yeah, and so so I was kind of hoping that it would use the index for the department employee table, but it still doesn't seem to be doing it. So I'm gonna have to keep trying. Okay, so the next big obvious table is this salary table, which we know is being used right here. And so let's go ahead and create an index for that one too. Okay, and so the index I'm creating for it is using the employee ID, to date, and amount columns. I'm going to create that index. Okay. Waiting for the, all right, so that took 36 seconds. Okay, let's see if it hits our indexes this time. Okay, now we're down to 4 seconds. That's slightly better. And look, it's using an index. I think that's generally better. Yep, so an index-only scan. That's nice. See, that's what you're looking for, indexes. But it's still doing a sequential scan on the department employee table. Well, okay, well, anyway. So so what I'm doing here is I just rewrote the function to be so that the subqueries here align perfectly with the indexes that we're trying to hit. And so what we're doing here is we have one query that will match up directly with the index that we created for department employee, and then another query for the salary table, which again will hit the index because it's explicitly written to use that specific index. And then when I run this query, by actually selecting it, it comes back almost instantly. So again, use your indexes, you'll be doing great things. Thank you.